So what we have discussed so far in this lecture is that we are interested in computing in general expectation values of some time dependent operator between some arbitrary states. And we have reduced this problem to the problem of computing just the vacuum expectation value. So the vacuum expectation value of some bunch of operators. This we discussed in the previous lecture. Okay, so at this point the goal is to compute them. And then also in the previous lecture we discussed something called propagator of two phi fields, phi 1. So this is simply just the 2-point function. And then we discuss various type of propagators. So for example, Whiteman propagator, then retarded, advanced, and Feynman propagators. But we've also found that this is the most basic thing. All others, this can be written in terms of Whiteman propagators. Okay, so this means that now that the topic of this lecture is to how to connect these two. So the topic of this lecture is how to use propagators to compute this vacuum expectation value of O1 T1 ONTN. Okay, and this connection is usually known as Wick's theorem. Okay, and we will discuss it how. So the first statement is that the vacuum expectation value of normal ordered operator is 0. Unless it's an identity operator. Okay. Why that is the case? Let's say we have some operator, that is a vacuum, and there is some normal ordered operator, completely normal ordered operator. So sorry, we should use our standard convention. Now, since this is not identity, then it is some polynomial of an and a dagger. Okay, so because if it's not identity, then it is some polynomial of a daggers. Because it is normal ordered, then is appear on right and a daggers appear on left. And that means that let's just consider an example. So in general, this will be something like sum over c power n1 comma n2. So in general, these operators, any normal ordered operator can be written in terms of this way: a dagger power n1, a dagger power n1, a power n2, with the condition that n1, n2 n1 and 2 are non-negative integers, and secondly n1 plus n2 is not equal to 0. Okay, so there at least one of them is non-zero. Then if we have this, then if we try to compute the vacuum expectation value of this, because A acting on vacuum is 0 or A dagger acting on vacuum is 0, this implies that whenever we have normal ordered operator, normal ordered non-identity operators, this always gives us 0. So this is operator set. So this is the first statement, that the vacuum expectation value of any completely normal ordered operator is 0. Okay. Now note one thing. If we have, say, two normal ordered operator, then in general, there may be some special particular cases, but in general, okay, so here I have taken, first I have taken normal order, then I have taken product, and this is not same as first taking the product and then taking the normal order. Okay, and the relation between this thing is precisely Wick's theorem. How to write? Because see, if we have a string of operators, if we have product of normal ordered operators, normal ordered operators, and if we can write them as normal ordered sum product operator, then we can use result 1 we can use result 1. So what is result 1? This I called result 1. Then we can use result 1 to compute okay. So let's first demonstrate this. Let's first demonstrate this with phi and phi. So phi, normal ordered phi is simply h bar by 2m normal ordered a plus a dagger. Okay, we are just not using time. We are not using the time dependent just for simplicity. But the result holds true for any time dependent operator as well. And this is same as h bar power 2m a plus a dagger, because normal ordered of any one of them is this. Now what is normal ordered phi square? Normal ordered phi square is h bar power 2m a plus a dagger square normal ordered, which is, sorry, this is square. So this is h bar power 2m a square plus a dagger square plus 2 a dagger a. This happens because it is normal ordering, okay, because it's inside the normal order. Whereas phi square is simply h square by 2m a square plus a dagger plus a dagger a plus a, which is same as h square by 2m a square plus a dagger square plus 2 a dagger a plus 1. Okay, so which is same as then phi square normal ordered plus h square by 2m. So what we found? We found that if I take the normal ordered phi, this is same as normal ordered phi square plus h square by 2m. Okay. Now let's just for make the case, let's just also understand what happens in the time dependent scenario. So in the time dependent scenario, phi I t normal ordered, this is simply h bar by 2m a exponential im minus imt plus a dagger exponential imt. Okay. Now let's try to compute phi I t1, phi I t2. Okay. So if I want to compute this quantity, then this quantity becomes h bar by 2m a exponential imt plus imt1 plus a dagger exponential t1, sorry, this with a exponential imt2 a dagger exponential imt2. Now you can easily do this computation, and this just becomes h bar power 2m. So if I take this becomes a square exponential minus im t1 plus t2. Then if I take this 2, this becomes a dagger a exponential im t1 minus t2. Then if I take so first we have done this and this, then we have done this and this. So now let's do this and this. So this becomes a dagger exponential minus im t1 minus t2, and now let's take this and this becomes a dagger square exponential im t1 plus t2. Okay, now let's you can see that this is almost same as the normal order thing, except this is not good. So this can be then written as h bar by 2m a square exponential minus im t1 plus t2 a dagger square im t1 plus t2 a dagger a exponential im t1 minus t2. From this term I get, if I change the order, this becomes a dagger minus im t1 minus t2 plus h bar by 2m exponential minus im t1 minus t2, and this just got by when I interchange these two things. When I interchange these two things, this gives rise to this term and this term. Now you probably can identify this result. So this whole thing is normal ordered phi I t1 phi I t2. Okay, this you can check. And this thing, the extra thing that we have got in this process is simply the Weightman propagators. Right? So this thing is just simply d t1 minus t2. So what we have done, we have shown that phi I t1 normal ordered, phi I t2 normal ordered is same as phi I t1 times phi I t2 normal ordered plus the Weightman propagators. Okay, so this is the simplest case. This is the simplest case of what is known as Wick's theorem. So the way it is done, in order to do that, in order to do these things, what we have to do is that what usually is the following thing. So first, the way Wick's theorem is done is first they define something called contraction. What is contraction? So contraction of is usually denoted in this way, and this means just the Weightman propagator between these 2 points. Okay, and then it is written as that is completely normal ordered plus contraction. Okay, so what is defined by that? By the contraction means it just you have to take the Weightman propagators between these 2 points. Okay, now let's statement of Wick's theorem. So statement of Wick theorem is that, let's say you have a bunch of operators, phi1, t1, phi2, sorry, not phi2, phi I t2, phi I t3, dot 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 phi I tn. Then this thing is same as firstly the full normal ordered thing, plus, let me first write this, t1, ti, all possible contraction of two operators. So all possible, I will write single contraction. Then you will have all possible two contractions. So this is one type of two contraction. Another type of two contraction can be like this. Plus all possible three contractions plus dot 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 up to all possible maximum number of contractions. Okay, so this is the statement of Wick's theorem. We will prove it, but let's discuss again. So in this case, what happened is that we saw that we took two normal ordered operator, and this became just this thing just became just completely normal ordered operator, and then this contraction which gives us the propagator. So this gives us Weightman propagator. Now the statement of Wick's theorem is that if you have string of normal ordered operators, let's say you have n of them, then first you take the completely normal ordered thing. Then you take the completely normal ordered thing, but up to that there are all possible single contractions. So this is one contraction shown, this is another contraction shown. There can be many type of single contractions, all possible single contractions. Then you have to take all possible two contractions, and this way you have to continue until you can do the all possible maximum number of contractions. Okay, so this is the Wigner's theorem. Not Wigner's theorem, sorry. This is called Wick's theorem. We will prove it. We'll prove, and then we will show that how to use this result to compute basically these quantities. So in order to, how we'll show that how to use this result to compute these quantities. Okay.